Good morning to Dr. Shakina and all my fellow classmates. So today we are from Group 4 project members. We would like to present about Engineering Mathematics 2 project assignment. So let's start by introducing ourselves. My name is Tan Suja. My metric number is 200518.
Hi everyone, my name is Sneha and the matrix number is 200967.
Hi, my name is Nur Adina Izati and my metric number is 200,368.
Okay, Ken.
Okay, the topic for our presentation today is first order ordinary differential equations. We call it ODE Application Problem. So we have done with introducing ourselves. And next, the instruction given to us for this project assignment is based on ECH 3115 project, develop a mathematical application problem to solve the first ordinary differential equations ODE based problem by applying what we have learned using one of the following methods. So the first method is substitution via reduction to separation variables. The second method is substitution via Bernoulli equations. And the third method is integrating factor method. And the last method is radiation parameter method. So our group have decided to choose the equipment as our design problem, which is crude acetic acid tank. The application problem we design is in an acetic acid production plant, a crude acetic acid tank is placed in the halfway of the production line. The crude acetic acid tank functions as a storage tank which temporarily stores the crude acetic acid before it's being further purified and processed into anhydrous acetic acid, which is the final product to be sold. One day, the production plant is shut down for routine maintenance and repairing of leaking pipe, as shown in figure 1.1. During the shutdown, assume the crude acetic acid tank contains 100 meter cubic of crude acetic acid solution, in which initially 20,000 kilograms of acetic acid is dissolved in it. As the production of acetic acid begins as usual, crude acetic acid solution containing 188 kilograms of acetic acid per cubic meter is allowed to flow into the tank at a rate of 497 meter cubic per hour. Assume that the concentration of the acetic acid in the solution is uniform throughout the tank. The well-mixed solution then flows out of the tank at the same rate of 497 meter cubic per hour. Okay, so the volume flow rate in and out is derived from our energy balance project mass flow rate divided by the average density of the solutions. So the questions we design is question A, determine the amount of acetic acid in the tank at any time t. Question B, how much of the acetic acid is in the tank after 5 hours? Next will be continued by Sneha.
Thank you, Shujia. So this is the figure 1.1 that Shujia has explained a while ago in her question. As you can see in this slide, the crude acetic acid tank has a volume flow rate of 497 meter cube per hour entering the crude acetic acid tank, and also 497 meter cube per hour of acetic acid tank leaving the crude acetic acid tank. So for the next slide. Okay, so now let's discuss about the solution for question A. So the question A is actually determine the amount of acetic acid in the tank at any time t. So to solve this solution, the first step that we need to take is to let y t denote the amount of acetic acid tank at any time given at any time t. So the differential equation involved in this problem is given by, as you can see the equation here, rate of change of y equals to the rate of change of the rate of which Y enters the tank minus the rate at which Y leaves the tank. So to put it in a much more simpler way, it is dy per dt equals to input rate minus output rate. So next. Okay, so the next is that as we discussed in the previous slide, input rate minus output rate, where the volume flow rate entering the crude acetic acid tank is 497 meter cube per hour, and the concentration of solution in flow would be 188 kilogram per meter cube. So by then we can calculate the amount of acetic acid entering the tank with the volume flow rate inside entering the tank multiplied by the concentration of solution, which equals to 93,436 kilogram per hour. The same method that we're going to be using to calculate the output rate, but however, we do not have the concentration of solution for the outflow of the acetic acid from the crude acetic acid tank. Therefore, as you can see here, we have written as YT over VT. However, we do know the flow, which is 100. Hence, we can use this to multiply and also find the algebraic output rate. So to continue the problem, we can actually see that the initial value problem for this situation is as written as in the equation, where dy per dt equals to 93,436 minus with 4.97 YT, where Y initial rate equals to 20,000. And rearranging this equation into the form of non-homogeneous linear first ODE, you would get this equation where dy per dt plus 4.97 YT equals to 93,436. This is in the form of non-homogeneous linear first ODE, also with the initial rate at 20,000. So when we derive all this equation and solve it, we can get that fx equals to 4.97, whereas rx equals to 93,436. So next. Okay, so as a step to solve the non-homogeneous linear first ODE, we are using the variation parameter method as it's the most suitable method to solve our particular question. So for the first step of this variation parameter method, we're going to change the ODE into homogeneous linear ODE by letting Rx equals to 0. Letting Rx equals to 0 is the variation parameter method. So as you can see in the slide, it's dy per dt plus 4.97 YT equals to 0. And we can solve the ODE. Well, we're getting the answer as ln y equals to negative 4.97 t. Okay, so next, Atrina will be continuing the presentation.
Okay, next for step 2, we're gonna change we're gonna construct a solution using non-homogeneous ODE by using parameter equation, which is by substituting the value y that we give just now into the equation. So the new equation will be yt equal to e to the power of negative 4.97t plus vt, and we need to do the dy dx differentiation by using product rule to get the dy dx of the equation. Next, for step 3, is that we need to substitute the value that we got for dy dt just now and yt to the non-homogeneous ODE, which is the first one. So when we substitute, we need to make the dv dt as subject, and then we need to rearrange so that dv will be on the left side and dt will be on the right side. Next, we will integrate both sides so that we get vt. We will get the answer in the terms of vt plus t. Next. Next, for the step 4, because just now we integrate and we got the unknown c. So how we want to know the value of c? So the solution is that we actually need to substitute back the initial condition just now, which is y is equal to 20,000 when x equal to 0. So we will get c equal to 1,200. So the general equation that we got finally is yt equal to 18,000 plus 1,200 e to the power of negative 1.497.
With the solution for question B, let us recall what is question B just now. How much of the acetic acid is in the tank after 5 hours? So is just substitute t equals to 5 into the particular solution we obtained just now, which is y5 equals to 18,800 plus 1,200 e to the power of negative 4.97 times 5. Acetic acid in the tank after 5 hours is equal to 18,800 kilogram. Okay, so that's all from us. Thank you.